So today we're going to look at a linear slide with a Renishaw high-resolution sine-cosine encoder on the load with a 0.3 millimeter ball screw driven by a high-resolution stepping motor. We're going to drive the stepping motor open loop and close the load position with the sine-cosine encoder. So it's the Renishaw Tonic. I've just got a 24-volt supply powering the ME3 and disconnected with the serial cable. So we're going to look at the ME3 because it can drive a servo motor or a stepping motor. And the stepping motor will use sine-cosine on the load, open loop on the stepping motor. If we had a servo motor, we could do closed loop, but why not use a stepping motor? It's really good at holding position without servoing. That's always nice. The motor is an extreme accuracy stepping motor, which means it just has low resonance and it's not supposed to have as much detent as other motors, but I don't know, there's still a little mechanical backlash in the system here, so could be the detent or maybe not. Haven't tested that out yet. But we can see that this is 0.1 Newton meters, 3 ohms. Going to run it off a 24-volt supply. We don't need to go very fast, so it should be able to go at least 500 RPM. A ball screw. I love this video here. So the screw moves, the nut stays still, and the screw moves, or the screw stays still and the nut moves. But this is a ball screw, so there's these circulating balls in here, and it's very smooth, very precise, very accurate positioning. So that's a basic ball screw there. And then of course the Renishaw Tonic, there is an incremental version which are limited in speed of meters per second, which is 162 millimeters per second with incremental, or you can go 10 meters a second with the analog sine cosine. I don't know that we want to go that fast, but we could go much faster with a sine cosine. There's some cabling, incremental A naught, B naught with index pulse, and to get some power, or sine cosine. So this is sine cosine with a reference mark or a limit. And this is how you wire it up here to the 9-pin DSub that comes on the Renishaw. Good cabling, grounding, shielding. Everybody gets a path to earth. So there's outer shield, which should find a path to earth. And then there's an inner shield, which can go to the 0 volts, which is the return of the 5 volts. So with 2 shields, the outer shield goes to earth, and the inner shield can go to the 0 volts of the 5-volt return. That's good cabling, grounding, shielding. There's some termination in the drive, blah, blah, blah. Incremental pulses with a reference mark. And we can see the sine cosine. A sine wave has a period of 20 microns, and then divide by 4 to get the quadrature out of it. And then plus we interpolate that in the drive. And there's the reference marker. Nice digital pulse with respect to the 20 micron. So we look for the edge for the transition. So we're just going to do a little math here to see what the interpolation would be, divided by 4. And then divided by 1024 interpolation. And in engineering terms, it's about 5 nanometers, so 4.88281 nanometers per count, interpolated position count at the load. So we'll take a look at CME here, and there's a rule that we have to have for setting up the load with respect to the motor. So if the motor rotates 1 time and we have a 0.3 millimeter pitch approximately. What is the fundamental count from the perspective of the motor shaft? Well, if I rotate the motor one time and it's 20 microns and I go 0.33 millimeters, I divide these two numbers and I get 15. That's the fundamental count. So the resolution for the sine, being 20 microns divided by 4 or times 4 would be 60 fundamental counts. And with a 1024 interpolation, that's 61,440 counts per rev at the motor shaft. And so that's how we're going to do this from the perspective of the motor shaft. We're going to close the position on the load. So let's see how we set this up with CME. It's a stepping motor. It's a rotary motor. There's analog feedback, but I have to say it's on the motor. So I can do encoder corrections. And the fundamental line count at the shaft of the motor, when I rotate the motor one time, would be 15 times 4, and then times 1024. I get 61,440 counts per rev at the motor shaft, which is still a count at the load. So one count is still approximately 5 nanometers. And that's the basic setup there for that. And then we can see the basic data for the motor. And I set the microsteps per rev to the same as the counts per rev. So with a 0.9 degree, I got 400 full steps, and I divide that down, 61,440. 1 microstep will be 1 count at the load. This could be 10 times bigger if you want. That's fine. But I like to see my counts. 1 count equals 1 microstep, and it's just less confusing. But you can set this to 10 times if you want. That's fine. And again, there's the feedback. And so we tune the current loop for a good kilohertz or more of current loop bandwidth. The boost and run are set the same. The hold is lowered. So after the move is done, I get a little settling time here. But for this system, I'm doing hold the voltage mode because I want to take an image after the move is done, and I don't want the thing to servo while I'm trying to take my image. Just stand still. So we go from hold current to hold pulse width, which prevents the servo action from occurring, and I don't get any motion, and then I can take my image. So that's a nice feature there. The encoder corrections, gains are set. So as we move, if there's an error, it will correct at a certain rate. So that's all good. And I have some trajectory limits that we've tested and tracking windows that are set, and I don't bother me with a following error. So let's take a look and see how this thing looks for tuning. Auto setup checkbox, command and an actual. So I have a command and an actual. The current loop gains are set, so there's not too much overshoot, and there's some integration. So that's typical for stepper. That looks good. And then, so we're going to make a move. Single rev at the motor shaft, 61440. So they made a single move at the motor shaft, and it's reading trace data. But you can see that even though it moved and settled, that there's still some hunting going on. So the motor's moving plus or minus a little bit, trying to correct for a little play in the system. So even before we move, there's a little hunt of 25 counts back to 0. The move and settle looks good, but there's this continuing to hunt going on. That's within the mechanical limit of the system, plus or minus 25 counts. If we want to move and settle and stop hunting, we'll have to stop servoing. So that's what the hold the voltage time will do. So I'm going to give it another 25 microseconds. So voltage mode typically used to reduce jitter after stopping and holding position. Encoder corrections will not be made while holding position. Yes, I'm sure I want to do that. So we're going to try to get within 10 counts, and then we go from run to settle, and then after that we'll go to hold. We could do it immediately or wait for some time, and we'll see the effects of what we do. Okay, so I did move forward, move reverse, changed it to a 10 millisecond. So So let's take a look at this. So rather than do that weird hunting thing, it's just holding the pulse width of the microstep, and if it moves, it's just because it's an open loop thing, and it does tend to shift a bit, but that's we're open loop and we're just holding. So what goes on at the load is just steady state error. So moves, settles into 20 counts. So we got close, we held it, and then it just relaxed and settled. So these are mechanical effects of not being in a closed loop. But the move and settle does hold still. Take the image. Same thing with coming back, it looks pretty good. So you got a little bit of time to take the image, several seconds before whatever happens, drift or heat or vibration, whatever moves it out of its position, open loop. Okay, so that's the tuning of the motor on the feedback on the load with a stepper. If this was a servo motor, you could use the encoder on the shaft of the motor and do servo at the motor and then closed loop on the load. That would be a dual servo loop. But the steppers are traditionally done open loop because they're really good at being stepping motors. And that's it for today. Thanks for watching.